Hi everyone, welcome to the channel. I hope you all are doing great. So we were discussing about the previous year questions of the UPSC Geoscientist exam, and in that the physical chemistry portion we have started, and the chapter we were discussing was your electrochemistry. So the first part of it we have already discussed, in which some of the questions we have discussed. Now this is gonna be the part number 2 in this series of the electrochemistry chapter, where the remaining questions we are gonna cover. So these were the questions that we discussed in the last class. So if you have not watched, playlist is there on the channel, you can check that. Okay, so now let us begin with the next questions of this one. Okay, so these were the questions that I gave to try it firstly yourself and then look to the answers. I hope you have tried this one. So now we will be discussing the solutions to these questions. So this question it says to us is that a potential of 5 volt is applied between two of the electrodes which is placed 10 centimeters apart. Okay, how far uh, would a sodium ion be expected to move in 1 hour in a dilute solution of the sodium salt at 25 degrees centigrade? Okay, so that means distance we have to find it out. Time it is given that in the 1 hour the sodium ions they are traveling. So potential how much we have applied is that is of the 5 volt, and the electrodes distance between them it is also given to us. Okay, so we know that mobility that we denoted with the mu, this is equal to the ratio of the ionic velocity, that is the velocity with which your ions are moving, upon the potential gradient. Upon the potential gradient. Potential gradient is nothing. It is just the potential that you are applying per unit length. Okay, so this is will be equal to the, now this is velocity, I am denoting it with the V, and the potential gradient. So this you write it completely, because volt also you will be using this V term only. This is volt per unit length. This is the formula for your mobility. One more formula you have for the mobility, that is equal to the lambda, that is lambda naught basically, that is your conductivity at the infinite dilution upon the Z, which is the charge on the ions, into the Faraday's constant. Okay, so these two formulas that we are having for the mobility, this we can equate, because velocity is nothing but your velocity, or we can say this is my speed. It is in chemistry, velocity and speed we consider it to be the same. Otherwise, velocity is displacement per unit time and speed is the distance per unit time. Okay, so here we have to find this the distance, so that I am keeping, and upon the time that is already given to us, that for 1 hour our sodium ions they are moving. Right. So these equations we will be making use now. So lambda upon the z into the f, it is equal to the velocity, that is distance, upon the time, upon the time, and here you have the potential per unit length. Just substitute the values in these now. Okay, so lambda value, that is at infinite dilution, it's already given to us. It's 50 Siemens centimeter square per mole inverse. So 50 Siemens centimeter square per mole inverse upon the Z, which is the charge on the sodium ion, which is equal to the 1 unit, right? So it will be 1 into the Faraday's constant, which is your 96500, right? And this is equated to a distance upon the time. Time here it is given to us, that is 1 hour. This 1 hour we have to take it into the seconds. So 1 hour is 60 minutes and 1 minute is 60 seconds. So in seconds the time we have to put it. Next we have is potential upon the length. Potential applied is of the 5 volt and the length is 10 centimeters. So it is 5 volt upon the length, that is my 10 centimeter. So we just have to solve this one. Okay, and solving this, the distance that you will be getting, it will be coming out in the centimeters, and that answer you are gonna get it as 0.93 centimeters. So just do the calculation part now. You will be finding your answer. Okay, I have already solved it and I have got this much distance. Right? So this is given to us in the option B in this case. So the main thing is these formulas for the mobility you have to remember. Direct questions will be coming from this topic. Okay. Now moving upon to the next question. This also I gave to try it firstly yourself. So I hope you would have tried this one. Now check your answers. So it says statement based question you are having, that is consider the following statement regarding the Walden's rule. Now Walden's rule we have already studied that according to the Walden's rule, the conductivity into the viscosity of the solvent. This is your conductivity, conductivity, and this is your viscosity of the solvent, viscosity of the solvent. This product that you have, this product it comes out to be a constant value. This comes to be a constant value, and this is what your Walden's rule it states, and this is applicable for the large sized ions. Reason why it's not applied on the small ions is that because the small ions they have the high charge density. So due to that they get solvated to a larger extent and hence the viscosity of the solution it is gonna increase. That is solvation shell which is present around the ion, its size it is increasing, due to that the viscosity it is increasing. So this product which we are getting, it's not gonna be the constant in that case. It's gonna be varying. Okay, so it's applicable to the large ions only. So based upon this, the statements it is given to us. The first statement we are having is Walden's rule is not applicable to the ions of the small size. This I told it's your true statement because it's applicable to the large size ion because they will be having the less charge density, so less solution of these ions it will be taking place. Right. Statement 2 it says small sized ions have the high charge density, as a result they are highly solvated. This statement is also your true one, and in fact second one is the correct explanation for the first one. So where the correct answer it becomes both the statements are the true and statement 2 is the correct explanation, that is the option A in this case. Okay, moving upon to the next one, this question where you have consider the following graphs which is showing the variation of the molar conductance with the concentration. It's under root it's given to us. So 1 and 2 we have to predict the electrolytes which is showing this plot, that is the first one and the second one. So molar conductance versus the concentration. The first plot you can see that we can extrapolate this curve to get the molar conductance at the infinite dilution, and this is possible only for the strong electrolytes. This is possible for our strong electrolytes, right? This is our strong electrolytes. Electrolytes. Strong electrolytes means the one which shows the complete dissociation into the ions. Example you have is KCl, you have the NaCl. These are my strong electrolytes which is gonna completely dissociate into the ions. Whereas the second plot if you see, if you extrapolate this like this, it is gonna go that is going in the parallel direction to the molar conductance. For this we cannot find the this molar conductance at infinite dilution, that is it is for my weak electrolyte. That is the one which shows only the partial dissociation. Example is the acetic acid, ammonium hydroxide. These are my weak electrolytes, right? So the first one is the stronger one. So from the options you can see in the option A, first is showing the plot 1 is for the KCl and plot 2 is for the acetic acid, which is our correct one because KCl is our strong electrolyte and acetic acid is our weak electrolyte, right? In the others if you see B scenario, both are given as the weak electrolyte, so this can't be the answer. In the C, it is first one they are saying that it is acetic acid. No, that is again the wrong one because the strong electrolyte it is given. In the D case, both the strong electrolytes are given to us. In the plot 1 and 2 they are saying that is again becoming our incorrect. So the first A is the correct option this case. Okay, moving upon to the next one. This question you are having. So amide ions in the liquid ammonia, it has abnormally high transport number. Why is it so? So here you might have studied for the water, the ions that you have, that is your H positive and the OH negative, they in the aqueous medium, that is when we are having them in the water, they are having the higher conductance exceptionally. Reason for that is, it is because proton jump it takes place in this. Because the solvent molecules, that is of the water you are having, they are providing a path for these ions movement. Now similarly for the ammonia solvent, if you see, here the ionic species which is present, so the gain of one of the ammonium ion and the NH2 negative it will be there. So these are the two of the ions you are having. Among this we are talking about this amide ions, right? So amide ions that I am having, so amide ions, they are going to have the higher conductance exceptionally. Reason for that, it is again your proton jump. The solvent molecules will help this ion to move in the forward direction. Due to that, their transport number it's gonna be high. So it's proton jump from one ammonia molecule to the other. That is why this amide ions can move easily. C is the correct answer. Next is we have this numerical. So it says resistance of this much molar solution of electrolyte, which is occupying a volume between the platinum electrodes of the cell constant 39 meter inverse is 30 ohms. Specific conductance and equivalent conductance we have to find it out. So we know that R is equal to the rho L by A. If I bring the rho in the denominator, it's gonna be 1 by R into the L by A. 1 by rho it's nothing but the kappa, which is my specific conductance. Substitute the values of the resistance that is given to us as 30 ohms and the cell constant, which is 30. Just a second, 30 ohms we are having, and the cell constant is 39 meter inverse. Solving this, the value we will be getting at 1.3 meter inverse ohm inverse. This is gonna be the specific conductance. So this is your specific conductance. Now you have to find is the equivalent conductance. So for the equivalent conductance, we know it is kappa upon the normality. Here you will be having normality. So here the kappa value we have got it as 1.3 ohm inverse meter inverse. Normality, or the here the concentration it's given to us as 0.1 molar. So this concentration term it is given, so we can consider the n factor equal to the 1 only, and molarity and normality can consider it to be the equivalent only. So this is gonna be 0.1 mole, or the gram equivalence you can say, because normality we are considering. So number of the gram equivalents per liter. This is gonna be the concentration term. Now here you are having is the unit of the meters, and here is this liter term we are having it. So convert this liter into the meter cube. So for the conversion, we know that 1 meter cube it is equal to the 1000 of the liters. So 1 liter it will be equal to 10 raised to the power of minus 3 meter cube, right? To substitute this in place of the liters, we will be getting it. This is ohm inverse, meter inverse upon the 0.1 gram equivalence. For the liter, it is 10 raised to the power of minus of 3 meter cube. This in the inverse we are having it, right? So solving this, we will be getting it like this: 1.3 ohm inverse, meter inverse. Here it's gonna be 0.1 into 10 raised to the power of 3 per meter cube. Here the gram equivalence term it was already present. So answer we will be getting in this case at 0.013 Siemens meter square per gram equivalent. You can write either the ohm inverse or the Siemens over here. So this is gonna be the value that is for the equivalent conductance we will be getting here. So the specific conductance is my 1.3 and the other one is 0.013. So the correct match is given to us in the option B. Specific conductance we have got is this much and the equivalent conductance we have got is this much. Okay. Next is you have this question. It says the conductivity and the molar conductivity of a saturated solution of a barium sulfate are this and this. What is the KSP for this? The conductivity, that means kappa value, it is 3 into 10 raised to the power of minus of 6 Siemens per centimeter, and the other is lambda n, which is given to us as 150 Siemens centimeter square per mole inverse. So we know that lambda m it is kappa upon the concentration. Concentration will be kappa upon the lambda n. So this is 3 into 10 raised to the power of minus of 6 Siemens per centimeter, and here it is 150 Siemens centimeter square per mole. So with this Siemens is getting being cancelled out, so it is 50, and this is gonna be 50 it is there. So it will be 0.2 into 10 raised to the power of minus of the 7 units. We are getting it as mole per centimeter cube. Mole per centimeter cube. But we need to convert this into the liters. So we know that 1 meter cube that is equal to the thousand of liters, and 1 meter is equal to the hundreds of the centimeter. So 100 cube it will be there. This is in the centimeter cube we will be getting. This is equal to the thousands of liters. So we can say that 1 centimeter cube, this is equal to 10 raised to the power of minus of 3 liters of it. Right? So this substitution you can make it. So we are getting it 0.2 into 10 raised to the power of minus of 7 mole per centimeter cube. It is there. In place of this centimeter cube, it's gonna be 10 raised to the power of minus of 3. This is minus 1, and this you are getting it in the per liters term. Right? So this is gonna be 0.2 into 10 raised to the power of the minus of the 4. This is in the mole per liter or molarity concentration we are having it. Right? So next is we have to find is the KSP. So barium sulfate, it's gonna give us barium 2 positive plus the sulfate ions. The solubility for each of them is S and S only. KSP will be the barium 2 positive concentration into the sulfate ions concentration, which is equal to the S square. So concentration term we are having is 2 into 10 raised to the power of minus of 5. Its square term it's gonna be there. So we will be getting the answer 4 into the 10 raised to the power of minus of 10. This is gonna be the KSP value. Okay. So the answer is C in this case. 4 into 10 raised to the power of minus of 10. Right? So I hope this is clear. So unit conversion is important in these type of equations. Moving upon to the next one. Again the numerical base. The molar conductivity of the acetic acid solution at infinite dilution it is this much. The molar conductivity of 0.01 molar acetic acid solution is, where the dissociation constant value we are having is this much. We are having the dissociation constant. So we have been given as dissociation constant, that is Ka value, it is given to us 1.8 into 10 raised to the power of minus of 5. So for any acid that is dissociating, it's gonna give you H positive plus the A negative, right? Initially it is of the C concentration and these are not dissociated. So after that, sometime if alpha is the degree of dissociation, this much extent of the H8 is gonna dissociate. H positive formed will be C alpha. A negative formed will be also your C alpha. Now to write the dissociation constant for this, It's gonna be the concentration of the products, which is H positive into the A negative upon the HA. Alright, this is gonna be C alpha into the C alpha upon the C minus of the C alpha. Alright, this is C square alpha square upon the C times of the 1 minus alpha. So this we get it as C alpha square upon the 1 minus alpha. So generally we consider alpha value to be very small. So 1 minus alpha is generally considered to be equal to the unity only. So from here we can say that Ka is equal to the C alpha square. Right? So from here you know the value of this concentration term. Ka value is also known. Alpha you can find it out from here. So now alpha value will be equal to the root of Ka by the C. Dissociation constant we are having it as 1.8 into the 10 raised to the power of minus of 5, and concentration value it is 0.01, 0.01. So this is two decimals are going in the numerator. So you can just find the answer to this. 1.8 into 10 raised to the power of minus of 3. This is gonna give us the alpha value. Right? Now we know that alpha it is equal to the lambda n upon the lambda n at infinite dilution. This is root of 1.8 into 10 raised to the power of minus of 3. So from here the molar conductance of 0.01 molar, this electrolyte solution we can find it out. Multiply this with the infinite dilution value that is already given to us. So here the value at infinite dilution is 390. So it is 390 into this particular factor. So here you will be getting the answer. Okay. So solving this, the answer we will be getting it as 16.54. You will be getting it as 16.54 Siemens centimeter square per mole. Molar moles. Okay. So this is gonna be your answer that is given to us in the option C in this case. Okay. Moving on to the next discussion. It says that in the conductometric titration for the HCl against the ammonium hydroxide, with the increase in volume of ammonium hydroxide, the conductance fell. So we are having this HCl versus the NH4OH. So this is your strong acid versus the weak base you are having it. So here what you are having is in the flask you are taking is the HCl initially you are having it, and its conductance is being noted, and from the burette that you are having it's filled with the ammonium hydroxide. So this is being added to it with the due course of time, and conductance change it is being noted. So the plot that you will be having it will be conductance, and here is the volume of ammonium hydroxide. So initially, since we are having the HCl molecules, the conductance it's gonna be high because of the proton jump that is present in the HCl. Now this HCl molecule it's being treated with the ammonium hydroxide. So the reaction that is taking place in that case is ammonium chloride, and along with that the water is being formed. Now the H positive ions are getting being converted to the water which remains undissociated. So due to that a decrease in the conductance you will be observing. As this ammonium hydroxide will be added, the conductance it's gonna decrease. Alright, a point will come when the equal number of this HCl and ammonium hydroxide equal moles we will be having it. At that point, they both have reacted. Now after that, ammonium hydroxide is being added to it, which is gonna show only the partial dissociation because ammonium hydroxide it is your weak electrolyte or the weak base we are having. So this type of the plot you will be observing. Alright, at this point where both of them they have become to be the equal, this you can call it as your end point, or you can say it is your equivalence point. This type of the curve you will be observing it. So here first fall and after the neutralization there is no appreciable change, that is in the option A we are having. Okay. Next is we have this. It says consider the following conductometric titrations of a mixture of the HCl and the acetic acid against the NaOH. The volume that is corresponding to the 1 and 2 are 6 ml. So here you have the volume 6 ml and here it is 16 ml. Alright. Respectively, what is the volume of any which used for the neutralization of the HCl and the acetic acid? So when you are having now this time in the previous case like in the flask the only HCl it was present. Now we are having this mixture that is of the HCl plus the acetic acid it is present, COOH it is there, right? And here from the burette the NaOH it is getting the added to it. This is NaOH we are having it. So here if you see the dissociation in this HCl molecule it's gonna dissociate to give the H positive plus the Cl negative and the acetic acid. Here it's gonna show the partial dissociation giving us the acetate ion and along with that this H positive. So here you are seeing that my strong acid is present in this case. That means it's gonna furnish a large number of this H positive ions. And due to that what is gonna happen, you will be observing the common ion effect in the acetic acid case because H positive concentration it is increasing. That means on the product side concentration it is increasing. So equilibrium it will shift in the backward direction. So due to the common ion effect, the dissociation of this acetic acid is further being suppressed. So firstly, this HCl molecule that is completely dissociating, it's gonna be reacting with the base that is NaOH we are adding to it. Okay, so in the first case, this is at the starting, both of the acids were present, but due to the common ion effect, as I am saying, this acetic acid dissociation is being suppressed. So the here the common ion effect is being applied. So HCl molecule, its dissociation it starts. So that is why you are up now HCl molecule will be reacting with the NaOH. So H positive is converting into the water which is undissociated. So decrease in conductance is there. That is till the point 1, that is all the HCl is being neutralized by the NaOH. Then comes the role of the acetic acid which will now be dissociating. So you can see not much appreciable change in the conductance you are observing till here and till there. This conductance value not much bigger changes there. So this is the dissociation for the acetic acid it is given to us. And after that, the NaOH that is further added due to that the increase in the conductance we are observing it. So till the point 1, if you see here only the neutralization of the HCl it was taking place. So till the point 1, only HCl is neutralized. HCl is neutralized. But at the point 2, if you see, now HCl has been neutralized in here and along with this acetic acid has also been neutralized. So at the point 2, both the HCl plus the acetic acid, they have been neutralized. Is neutralized. So for the HCl, the volume of the NaOH used is this much, that is your 6 ml. So for the HCl, the volume used is the 6 ml, whereas for the HCl plus the acetic acid, this complete volume you are having, this complete volume till the point 2, this is your 16 ml. This is your 16 ml. That means for the acetic acid, the volume used will be 16 minus of 6, which is gonna be the 10 ml. Okay, so 6 and the 10 ml that is given to us in the option D. I hope the concept is clear. Now moving upon to the next, we have is this question. It says, which of the following statements is or are correct regarding the indicator electrolyte in a moving boundary method which is used to determine the transport number of the ion? So two of the conditions in the last class also we have done the question related to this. So in the moving boundary method, You have two of the electrolyte solutions. One is called as the indicator electrolyte, indicator, and other is called as the principal electrolyte, principal electrolyte. In both of them, the anionic species it should be same. Anion, it should be same in both of them. That is the principal and the indicator electrolyte. Whereas about the cation, if you see the cation which is present in your indicator electrolyte, it should move with the slower speed. Cation of the indicator electrolyte, it should move slowly as compared to the cation of the principal electrolyte, as compared to the principal electrolyte. This is comparing their speeds. Okay, so this is the condition set for the moving boundary we have to remember. And one more, that was the formula from the head, that also the question based upon that we have seen in the last class. So you can refer to the previous, that is a part 1 of this chapter. Okay, there that questions have been discussed. So here the statement it says the anions it must be different in both the indicator and the principal electrolyte. This is your incorrect. Now only told that anion it should be the same in both of them. Next is the cation, that is of the indicator electrolyte. It should move slower than the cation of the principal electrolyte. This is your true one, as I told. Next is indicator electrolyte. It should be more dense than the principal electrolyte. This statement is also your true one. So second and the third are the true. That is in the option C it is given to us. Okay. Next one you have is this question. It says the solution which is of the 0.01 molar electrolyte with the conductivity this much, it is placed in a moving boundary cell that is having the area of this much. It was electrolyzed for 45 minutes with the constant current of 3 milliamperes. What is the transport number? So we know that the transport number of the cationic species, that is A positive, it is gonna be area into the length into the concentration upon the Faraday's constant, that is upon the current it will be discharge it will be there, which is equal to the I into the T, and here your Faraday's constant it will be also present. Right, so area into the length into the concentration into the Faraday's constant upon the charge, which is your Q is equal to the I into the T. So just substitute the values. Area we are having is, that is 3 centimeters square. Length we are having is 2 centimeters. The concentration we are having is 0.01. This is in the mole per liter, and the Faraday's constant, that is 96500, that is charge coulombs per mole it will be there. Right, upon the current, that is 3 milliamperes. So 3 into 10 raised to the power of minus of 3 amperes into the time, that is of 45 minutes. So this is gonna be converted into the seconds. Okay, so this liter one that is present, and here it is in the centimeter. So again this conversion we have to make it over here. The rest you can see with this per mole, this per mole and mole term will get cancelled out. This current, that is charge overall you will be getting this current into the time. So coulomb and this coulombs term it will get cancelled out. So we will be having a centimeter cube over here, and here is liter inverse. So this liter inverse we have to convert it into the a centimeter cube. Okay, so as we did the conversion previously, that my 1 meter cube that is equal to the thousands of liter. So this is your 100 centimeter, and this is cube, so thousand of the liters. So we can say that this 1 centimeter cube, this is gonna be equal to 10 raised to the power of minus of 3 liters, or 1 liter is 10 raised to the power of 3 centimeter cube. So this conversion, when you will be substituting in this, the transport number you will be getting it as 0.71 over here. Okay, so the correct answer is the option C in this case. Now moving on to the next one, we have is this again statement based it's given. It says which one of the following statements regarding the transport number of the chloride ions is the correct one. The transport number of the chloride ions in the aqueous solution of HCl it is lower than the transport number of the chlorine ion in the aqueous solution of NaCl. So you are having two of the solutions, HCl and the NaCl. The transport numbers here it is gonna be transport number of the H positive plus that of the Cl negative. Their sum in the electrolyte it's gonna be equal to the unity because transport number is nothing, it's just the fraction of the charge which is carried by your ions. So fraction sum of the ions which are present in the electrolyte solution it's gonna be equal to the unity, right? So in the HCl case, the transport number of the Cl negative it's gonna be 1 minus the transport number of this H positive, whereas in the case of the NaCl solution, we have its transport number of Na positive plus the transport number of chlorine negative, it is equal to the unity. So in this case, the transport number of chloride ion is 1 minus the transport number of this sodium ions. So now we know that the transport number of the H positive it's gonna be exceptionally high because of the proton jump, because of the proton jump present in the H positive, they are gonna carry the more amount of the charge. That means its transport number it is gonna be higher. So that means this value it is increasing. So overall transport number of the chloride ion it is gonna be decreasing. Whereas in this case the sodium positive ions you are having as compared to the H positive, its transport number it is gonna be lesser extent. So transport number of the chloride ion it is gonna be more in this case. So this statement that says the transport number of chlorine ion in the aqueous solution of HCl it is lower and that of the NaCl it is more. This statement is the correct to verify. Okay, so A is gonna be the correct answer in this case. Next is we have this again numerical question you are having. The conductivity cell it was calibrated using the zero point 0.1 molar KCl solution and measured resistance it was 100 ohms. Okay. The resistance of the same cell when it's filled with the different concentration of the KCl solution, this much ohms of the resistance we were given it. The molar conductivity of this second solution that we are having, it will be that we have to find it out. Given the conductivity, the kappa value that is for the zero point 0.1 molar KCl solution, it was this much. So we know that R is equal to the rho L by A because cell constant firstly we will be finding it, right? So here when the zero point 0.1 molar solution it is given, the kappa value it is given to us and the resistance value it is given. So it is your 100 ohms. Kappa value it will be in the 1 by because of the resistivity it's gonna be reversed 1.3 Siemens per meter we are having into the length by the area. So this cell constant we can find it out. So 1.3 into the 100. So it's gonna be with this ohm and this Siemens they will get cancelled out. So the cell constant it's gonna come out to be in the meter inverse. So cell constant. So we will be getting the cell constant value as 130 meter inverse. This is gonna be the cell constant. Right? Now, when you are having the solution which is your 0.02 molar, at that point resistance we are having is this much. Cell we have used the same, so the cell constant is gonna remain the same. So we can find the value of the specific conductivity firstly. So for the 0.02 molar solution, R again equal to the rho L by A. So we need is the kappa value which is gonna be 1 by resistivity that is gonna be equal to the 1 by R into the cell constant. So this time the resistance value it is your 500 ohms and the cell constant value it is 130 meter inverse. And here it is ohm value it is given to us. So this is gonna be the conductivity value in this case, and using this conductivity value we can find the molar conductivity. So the molar conductivity it's gonna be kappa upon the concentration. Kappa value we have find it out as 130 upon the 500, 130 upon the 500. This is Siemens per meter inverse, and concentration value we are having it as 0.2, 0.02. Molar conductance you have to find, so it is mole per liter. So convert this liter into the meter cube and find the values of the molar conductivity for this one. Okay. So on solving this, the answer we are gonna get is that is 130 Siemens centimeter square per mole inverse. Okay, so just do this conversions of the meters and this liter term, because the final answers that is given to us, it is in the centimeters. So 130 that is given to us in the option C over here. Okay. Moving upon to the next one we have is this question. It says the molar conductivities at infinite dilution for the nitric acid, the acetic acid and the sodium nitrate are this and this values. What is gonna be the molar conductance at infinite dilution for the sodium acetate? So we need to form is sodium acetate. For that we need is the ions, that is sodium positive and the acetate ions. So the acetate ion we are gonna get it from the acetic acid. So we need is the molar conductance at infinite dilution for the acetic acid, CH3, COOH. So this one we need to find this one. Okay, and we need is the sodium ion. So for that we need is the molar conductance of the sodium nitrate ions. Right, now along with this, the extra ions that is coming, that is of this hydrogen, that is from the acetic acid, and this nitrate ion is coming from the sodium nitrate. So the molar conductance at infinite dilution for the nitric acid, it has to be subtracted from this one. So just substitute the values now. For the acetic acid, the value we are having is 391, right? For the sodium nitrate, the value we are having it as 121.5, right? And for the nitric acid, the value we are having it as 421.2, 421.2. All of this is given to us in Siemens centimeter square per mole inverse, right? So just solve this. The value you will be getting it as 91.35 Siemens centimeter square per mole. So this is gonna be our answer that is given to us in the option B over here, right? Next is we have this one. It says the correct order for the molar conductance at infinite dilution for the lithium chloride, sodium chloride and the potassium chloride. So lithium chloride, potassium chloride and the sodium chloride. So they all will be in the aqueous medium we will be having, because dilution has been done. So all of this, they are differing in their cationic parts, that is lithium positive, K positive and the sodium positive, and these three differ in their sizes. So without solvation, if the sizes, if you see, without solvation, the size comparison, if I see, it's gonna be sodium, this potassium positive, it's gonna have the maximum one, potassium positive, it's gonna be maximum, followed by the sodium positive, and least one is gonna be for the lithium positive. This is without solvation. But being the smallest in the size, lithium positive, it has the high charge density. It has high charge density, whereas the potassium, it has the least charge density. Least charge density. So based upon the charge densities, the lithium positive, it's gonna be highly solvated, highly solvated, because it's gonna attract the more number of the ions water molecules towards itself due to the high charge density, and this one is gonna be least solvated. So for the solvated ions, if you compare the sizes, the lithium positive, it's gonna have the maximum, followed by the sodium positive and then the potassium positive. This is the size when they are solvated. Alright. So now if we compare their mobilities, mobility is gonna be inverse of the solvated sizes. Solvated sizes, that means the potassium chloride, it's gonna have the maximum, followed by the sodium chloride, and least we are gonna have it for the lithium chloride, right? So this is gonna be the order for the conductivity of these electrolyte solution: potassium chloride, sodium chloride, and then lithium chloride, that is given to us in the option B over there. Alright, next is we have this question. It says which of the following statements regarding the ionic molar conductivities. Statement 1, it says with the increasing dilution the conductivity it keeps on increasing, and statement 2, it says with the increasing dilution the degree of ionization of the weak electrolytes it increases, the mobility of the ions also increases. Both these statements are correct. The first one, if you see the molar conductance, it is kappa upon the concentration, and concentration is expressed in terms of the molarity, which is number of the moles of the solute upon the volume of solution in the liter. So volume, it's gonna come in the numerator if we are diluting it. So with that the volume of the solution it is increasing, and hence the conductivities it also increases over here. Molar conductivity it is increasing. Right? So first statement is the correct. Next is with the increasing dilution, the degree of ionization of weak electrolytes it increases. This statement is also correct. We have seen this curves. First one, that is for the strong electrolytes, that plot that you observe, that is molar conductance versus the root of concentration. Like this the plot you observe it. But for the weak electrolytes, this type of the plot you are observing. So with the decreasing concentration, that means suppose if we are going it on this side, with the decreasing concentration, a point is coming where you are seeing a sharp increase in the conductance it is there. The reason for that is the dissociation of the weaker electrolyte it's gonna increase. With this, for the strong electrolyte case, the reason was the ionic interactions. With the dilution, the ionic interactions it decreases. Due to that, the conductance it increases. But for the weak electrolytes, it is their ionization which is increasing. Okay, so both these statements are the correct, and 2 is the correct explanation for the first one. So this A option will be the correct in this case. Okay, next one we have is this question. It says regarding the Walden's rule, it is again there. So first statement, it says the Walden's rule it holds good for the tetramethyl ammonium ion. So tetramethyl ammonium ion and the picrate ion, these both are large sized ions. Right? These both are a large size ion, and for them the Walden's rule it's gonna hold good. So this statement is gonna be true one. Next statement, it says the defective radio tetrahedral ammonium ion and the picrate ion in the solvents are larger and very different from the crystallographic radii of the ions. So that means they are saying if you are taking them, the solvated ions if you are having, and the crystallographic sizes when you are observing, they are gonna be different. This is what they are saying, right? They are gonna be very different, but it's not the case. They will be having the similar sizes. Reason being, they are of the large size, and due to the large size, they are gonna have the low charge density. So due to large size, large they have the low charge density, low charge density. So their sizes, so the sizes when they are solvated and the crystallographic ones, crystallographic radii will be the same, we will be getting and not the different. So this statement is the incorrect. So first one is true and second is the false. That means option C is the correct answer in this case. Right? Next one we have is this question. It says consider the following statements regarding the movement of the ions. The ionic mobility is inversely proportional to the potential gradient. We know that ionic mobility it is velocity upon the potential gradient, upon the potential gradient. So the first statement it says that it's inversely proportional to the potential gradient. That is the true statement. Right, next is ionic mobility. It's directly proportional to the ionic speed. Again, you are seeing it's again the true statement, directly proportional to the velocity or the speed also you can say it. Alright. Next is transport number of the ions. It is inversely proportional to the ionic speeds. Transport number is the fraction of the charges that your ions are carrying, and it's directly proportional to the ionic speed, not the inversely proportional. So this statement is the incorrect one. Next is sum of the transport number of the ions in the solution. It's equal to the 1. This statement is true because transport number are fraction of the charges only, and fraction of the charges sum of all the ions when you take it, that is always gonna be equal to the unity. For example, if the sodium chloride solution, if you have it, in this the transport number of the sodium ion plus the transport number of the chloride ion, this sum is equal to the unity only. Right. So first, second and the fourth are the correct statement that is given to us in the option B. Right. So this is the correct answer for this one. Moving to the next one we have is this. The following graph variation of the molar conductance with the concentration of and is that means we have to find it out which one is gonna be this graph is corresponding to which of the electrolyte solutions. First one it's saying it is for the strong acid. Second one it's saying for the weak acid, third it's saying for the buffer, and fourth it's saying for the ethanol. So we know molar conductance versus the root of C. If it's going parallel to the direction of the molar conductance, this is for the weak electrolytes or the weak acids we will be observing this. So B is gonna be the answer in this case. Next you have is this. So again, from that graph only the questions is there. The first one it is for the strong electrolyte, and the second one it's for our weak electrolytes. So plot 1, in statement 1 it says, plot 1 it can be extrapolated to obtain the molar conductance at infinite dilution of the weak electrolytes. So it's not for the weak, it's for the strong electrolytes. Second one it says plot 1 can be extrapolated to the molar conductance at infinite dilution of the strong electrolytes. This is true because you can extrapolate it to find the conductance at the infinite dilution easily, and this is for the strong electrolytes. Next is plot 2, it can be extrapolated for the molar conductance at infinite dilution for the strong electrolytes. Neither it is for the strong electrolytes nor your curve it can be extrapolated. Right. Next is both plots 1 and 2 can be extrapolated. Again, the incorrect second one we cannot extrapolate it. So the correct answer is the option B in this case. Okay. Next one is this question. The term A under root C in the Horn-Sager equation, which is lambda, that is molar conductance at some other conditions, it is molar conductance at infinite dilution minus of the A plus of the B into the lambda infinity, this whole into the under root of the C you are having. So the decrease in the conductance from the infinite dilution, it is because of two of the reasons. One is the asymmetric effect and other is the electrophoretic effect. The asymmetric effect, it arises because of the solvent ions which are surrounding the particular ions, and when the electric field you are applying it, the ions they will be moving towards one of the electrodes, whereas the solvent molecules they move in the opposite direction, right? And the electrophoretic effect is because of the opposite ions which are surrounding it. Okay, so the term A under root of the C that you are having, it is because of this asymmetric effect, the decrease in molar conductivity due to the asymmetric effect, whereas B into the root of infinity, this is for the electrophoretic effect. So B is gonna be the correct answer in this. Right. Next one we have is this question. It says the molar conductivities of this much molar dichloroacetic acid is this much. The molar conductivities at infinite dilution for the HCl, NaCl, and for this sodium dichloroacetate are this and this. What is the degree of dissociation and the dissociation constant, that means the alpha value and the Ka value they are asking to us. So here this alpha value it is lambda n upon the lambda n at infinite dilution. Here the molar conductance at infinite dilution we have to find it out. The conductivity of this much molar dichloroacetic acid it is already given to us. That means lambda n value we are having it 3.88 into 10 raised to the power of minus of the 5. This one we need to find this out. Right. So now for this particular this electrolyte which is your dichloroacetic acid which means CHCl2 COOH. Right. For this we need is this ions and this H positive that you can get it. The anionic part it will be coming from the sodium dichloroacetate CH2COONA. This one we will be having. Along with this the HCl it will be there. The molar conductance at infinite dilution for the HCl we will be taking this molar conductance at infinite dilution we are finding. For the HCl it will be there and we need is the subtraction of the sodium and this chloride ions, that is conductance at infinite dilution for sodium chloride it will be subtracted. So just substitute these values, we will be getting this is 88 plus of 426 minus of 126. The value we are getting it as 388 Siemens centimeter square per mole. This is the value. Now the alpha value it's gonna be the ratio of this. So this was 3.88 into 10 raised to the power of minus of 5. This is in Siemens per centimeters. So this is the conductivity value it is given to us and not the molar conductivity. So this is not the lambda n. This also we have to find it out. Lambda m. This lambda m now finding out. This is gonna be kappa upon the concentration value. This kappa value we are having it as 3.88 into 10 raised to the power of minus of 5 in the Siemens centimeters. The concentration value we are having it as 0.001. This is mole per liter. Convert this liter to the centimeter cube. So after that you will be getting the value as 38.8 Siemens centimeter square per mole. So this is gonna be your lambda n and that is your lambda n at infinite dilution. So alpha value it is lambda n upon the lambda n at infinite dilution. So this is 38.8 upon the 388. Right. So the value we will be getting it as zero point 0.1. So alpha value is 0.1. Now we have seen this thing that dissociation constant Ka it is C alpha square. So concentration is 0.001 we are having and the alpha value we have got it as 0.1. Its square it will be there. Its square it's there. So we will be getting the value as 10 raised to the power of minus of 5. So alpha value is 0.1 and 10 raised to the power of minus of 5. That is given to us in the option D over here. So D is gonna be the correct answer for this particular question. Now moving upon to the next one, we have is this question we are having now. That is this. It says the conductivity and the molar conductance of the calcium fluoride at 18 degrees centigrade are this and this. What is the KSP for the calcium fluoride? So same type of the question like this we have discussed, that was for the barium sulfide. Now just the electrolyte solution they have changed it. So we need is lambda n equal to the kappa upon the concentration that we can represent as the solubility only. So S value it will be kappa upon the lambda n. So kappa is your 4 into 10 raised to the power of minus of 5 Siemens centimeters and the lambda n it is our 200 Siemens centimeter square per mole. So we will be getting the value in this as 0.02 into 10 raised to the power of minus of 5. This will be in the mole per centimeter cube. Right. or we can write it as 2 into 10 raised to the power of minus of 7 mole per centimeter cube. Now we need to find the solution, this value in the molarity terms, that is mole per liter we have to find it out. So now we know that 1 meter cube is your thousands of liter. So 10 raised to the power of 6 centimeter cubes, this will be equal to the thousands of liter because 1 meter is why 100 centimeters only. That means 1 centimeter cube, it is your 10 raised to the power of minus of 3 liters of it. Just substitute this per centimeter cube value, that is 10 raised to the power of 3. So 10 raised to the power of minus of 7 into 10 raised to the power of 3. This is in the moles per liter. So the value we will be getting it as 2 into 10 raised to the power of minus of 4. This is the molar concentration we will be getting it. Now to find the KSP, the calcium fluoride, if you see the dissociation, it's gonna be calcium 2 positive plus the 2 F negative. The solubilities of this is gonna be S and this is gonna be 2S. KSP for this is the calcium 2 positive concentration and the fluorine negative concentration raised to the power of its stoichiometry. This is S, this is 2S and its square. This will be equal to the 4S cube. That means 4 into 2 into 10 raised to the power of minus of the 4. Its cube it's there, right? So 32 into 10 raised to the power of minus of 12 we will be getting it, right? Or we can write it as 3.2 into 10 raised to the power of minus of 11. This is gonna be the KSP value that is given to us in the option B over here. Okay, so B is the correct answer in this case. Now moving upon to the next, we have is this. It says conductometric titration for the acetic acid versus the NaOH. That means weak acid versus the strong base. It's given to us. The area that is around this first curve, that is this slight increase in the conductance that you are observing, due to which of the reasons this increase it is there. So firstly we are having in the beaker, you will be having the acetic acid, so it is gonna be, it's your weak acid, so partial dissociation it's gonna show. So acetic acid, it shows us the partial dissociation. So H positive concentration, that is responsible mainly for the conductivity, it is gonna be lesser. So ions are less, so conductance value initially it is the less only. Now we are treating this acetic acid with the NaOH, with the NaOH. So due to that, what is happening? This H positive ions, CH3COO negative and Na positive. These H positive ions are being replaced by this sodium positive ions, which are larger in the size as compared to the H positive, and there is no proton jump for them. So conductance, due to that, it is gonna be decreasing. So a slight decrease, that is why you are observing in this case, right? Next is, you will be seeing the hydrolysis of this salt, it is taking place, and you will be seeing this in slight increase in the conductance because this is still your strong electrolyte as compared to your acetic acid. So more number of the ions you will be having. So due to that, this increase in the conductance we are observing. Okay, this is the slight increase. Then this in further, this neutralization it is gonna take place in further increase. It's because excess of this NaOH is being added to it. So around the curve 1 that you are observing, it's because of this hydrolysis of the acetate ion, sodium acetate, that is taking place. This slight increase in the conductance you are observing it. Okay, so B is gonna be the correct answer in this case. Moving upon to the next, we have is this. So a table is given to us that is showing the transport number of the cadmium ions in the cadmium I2, that is cadmium iodide solution of the different molarities. So when you see here, when the molarities are the lower, that is 0.05, 0.1 or the 1, 2.5, up to this the transport number value it is positive, whereas when you are increasing the molarities, the transport number values it is decreasing and it's becoming the negative. So what is the reason for this? Okay, so that's points we have to explain. So here you are seeing the positive transport numbers at the low concentration. So we have in the solution the ion status of the cadmium 2 positive, and we are having this ion negative. So this is my cation and this is my anion. And we know that the cations they move towards the cathode and the anions they move towards the anode. This is the general trend that we observe in the movement of the ions. Alright. So when they are moving this cadmium to positive, it is going to the cathode and the ion negative, it is going to the anode. At that point, the transport number values, it's gonna be positive in that case, and that you are observing in the dilute solutions. Alright. Whereas when you are increasing, so this scenario we are observing in the dilute solutions. When we are increasing the concentration, so for the concentrated solutions, it is observed that the transport number it is negative, which means that the ions this time they are going towards the opposite electrons. So we are expecting that the cadmium ions that is present, it is going towards the instead of the cathode now it is going towards the anode, and that is possible only when this cadmium 2 positive it has converted into some anionic part. So this is what happens in the concentrated solutions. It forms the ions like the cadmium I4 negative or the cadmium I3 negative it forms, or the cadmium I3 negative it forms. That is why it goes towards the anodic end, and the transport number you are getting it as a negative value you are observing it because towards the opposite electrode it is going. So this is the whole scenario in this. So in the statements you just have to check this thing. So it's saying in the first statement it says in the dilute solutions cadmium 2 positive ion it is migrating towards the anode. This is the incorrect because in the dilute solution cadmium ions will be migrating towards my cathodic end. So next is B statement is saying cadmium 2 positive it's migrating towards the cathode and I negative it's migrating towards the anode, and vice versa in the concentrated solutions, which means in the concentrated solutions they are saying cadmium ions will be migrating towards the anode and the I negative will be migrating towards the cathode. This is not happening again because in the concentrated solutions, the cadmium has converted to the cadmium I4 negative. That means these are the additional ions it will be present in the concentrated solution, which is going towards the anodic end. But the cadmium 2 positive, they are still going towards the cathodic end only. Cadmium 2 positive will be towards the cathodic end only, but just this new ions have been formed and the overall transport number that we get, that is the negative one. Okay, so this statement again becomes the incorrect. C statement it says in the dilute solution, cadmium 2 positive it's migrating towards the cathode, this much is correct. I negative it's migrating towards the anode, this much is correct. Next is in the concentrated solution, cadmium 2 positive it's migrating towards the cathode. This is what I said. And the cadmium I4 2 negative it is migrating towards the anodic end. This is again your true statement. So overall this statement is the correct one. So C is gonna be the correct answer in this. Okay. I hope the concept is clear. Now moving upon to the next question we have is this one. It says the transport number of the ions in a 1 molar solution of the AgNO3, it was determined using a zero point 0.3 molar solution of the cadmium nitrate in a moving boundary method. When a current of 15 milliampere it was passed for 30 minutes, the boundary swept through a volume of zero point 0.1 centimeters cube, the transport number of the Ag positive. So again, you are seeing that same concepts are being repeated in the boundary method. The transport number of the cations, it is area into the length into the concentration into the Faraday's constant upon the charge. Alright. So this area into the length, we can write this as the volume. Right. This we can write it as volume. So that value is given to us. So it is gonna be 0.1 centimeter cube. Concentration value we have been given it as 1 molar, right? So 1 mole per liter we are having, 1 mole per liter, and the F value it's gonna be 96500 charge, that is coulomb per mole we are having it. And in the denominator it's gonna be the Q value, which is gonna be equal to the current into the time. So the current value it is 15 milliamperes. So 15 into 10 raised to the power of minus of 3 amperes into the time, that is for the 30 minutes. So 30 minutes into the seconds you have to convert this. So this value we will be getting. So this coulombs we will be getting. This ampere into the time. This is gonna give you the coulombs. So this value and this coulomb will get cancelled out. This mole and per mole will get cancelled out. This is in the centimeter cube and this is in the liters. This conversion we just have to make in this, and after that the transport number we can find this out. The value we will be getting it as 0.357. Make sure the units, it should be unitless value of the transport number it's there. So just conversion of this per liter to the centimeter cube you have to make this. Okay, so this is gonna be the answer, that is 0.357, that is approximately 0.36. Option is the A in this. Right, next is we have this question. It says which of the following electrolytes it should be given to a chemist to be used as an indicator electrolyte in the determination of the transport number of Ag positive in the silver nitrate. So as I said, in the moving boundary method we have two of the electrolytes. One is the indicator and other is the principal electrolyte, and the anionic species in both of them it should be the same anion it should be present. So here the anion is your nitrate. So the indicator electrolyte it should also contains the nitrate ions. So that is present in the cadmium nitrate and in the lithium nitrate. Now we are measuring is the principal electrolyte is containing the cation, which is the Ag positive, and the indicator electrolyte it should be contain the cation which is moving at a slower speed. So cadmium 2 positive it would be the appropriate anion because it is of the slow speed. Slow speed. So cadmium nitrate is gonna be the correct answer. I hope it's clear. Anion it should be the same, but the cationic one indicator electrolyte its speed should be the lower one. So cadmium ion being the slowest in the speed as compared to the silver ions, this is gonna be the most appropriate one. Okay. Next one we have is this question. It says the ratio of the cell constant and the resistance is which of these? So we know R is equal to the rho L by A, the ratio of the cell constant. This is my cell constant, that is L by A, to that of the resistance. This is gonna be equal to the 1 by rho, that is nothing but the conductivity or the specific conductance. So this is your specific conductance. So that is given to us in the option, that is the B. So B is the correct answer for this one. Next is we have this question. It says the conductivity of a cell it was calibrated using the 0.01 molar KCl whose conductivity value is this much in a cell and measured resistance it was 700 ohms. When the cell is filled with the another solution, the cell had a resistance of this much. What is the molar conductivity of the other solution? So when you are having the 0.01 molar KCl solution, we are having it. At that point, the resistance we are having it as 700 ohms, right? And we are having the conductivity value as 1.4 into 10 raised to the power of minus of 3 Siemens per the centimeter. So using this, we can find the cell constant in which this experiment is getting being performed. So R is equal to the rho L by A. 1 by rho, it will be 1 by R into the cell constant. Okay, so we need is the cell constant. So that is R upon the rho value only. L by A is R upon the rho, that is nothing but the R into the kappa value, right? This is gonna be there. So resistance value is your 700 ohms and the kappa value is 1.4 into 10 raised to the power of minus of 3 Siemens per centimeters. So this and this will get cancelled out. The cell constant value we will be getting it as 0.98 centimeter inverse. This is the cell constant. Okay, next is for the another solution now, that is the AgNO3. For that, firstly we need to find is this conductivity value, because the resistance value it is given to us. To find the molar conductivity we need is the specific conductance. So the solution now when it is your 0.01 molar AgNO3, the resistance is my 800 ohms. Cell constants, it's gonna be, cell constant will be 0.98 centimeter inverse. So R is equal to the rho L by A, 1 by rho, which is nothing but the kappa. This is gonna be 1 by R into the cell constant. So this is gonna be 1 by 800. This is in the ohms, and the cell constant which is 0.98 centimeter inverse. So here the values you will be getting 0.001225. This is ohm inverse, centimeter inverse. This is gonna be the kappa value for this. Now we need to find is the molar conductivity for this. So lambda n is kappa upon the concentration. So this is 0.001225 upon the concentration, which is your 0.01 mole per liter, and this is ohm inverse, centimeter inverse. So again this conversion of the liters to the centimeter cube we need to make it. So for that it is gonna be multiplied with the 1000. So here mole per centimeter cube if you take it, here multiply it with the factor of 1000. So value you will be getting it as 122.5 Siemens centimeter square per mole. So this is gonna be the answer. So that is given to us in the option B over here. Okay. So I hope this one is clear. So the next question that we are having is this one. It says the molar conductivities at infinite dilution for the barium hydroxide, the barium chloride and the sodium chlorides are this and this. What is the molar conductance at infinite dilution for the ammonium hydroxide? So this one we wanted. And for this we need is the ion, that is the ammonium and the hydroxide. So ammonium ion we can get it from the ammonium chloride that is NH4Cl. Now along with this we need is the hydroxide. We need one hydroxide. So lambda n at infinite dilution for the barium hydroxide. So here two hydroxide ions are there. We need is only one. So we divide it with the factor of 2 in this case. Now the additional ions that are coming, that is barium and the Cl. This is the ions which is coming, the additional one. Half of the barium it is coming and one chlorine ion it is coming, chloride ions it is coming. So that means lambda n at infinity for the barium chloride it will be there. So divide this with the factor of the 2 and this is gonna be subtracted from that, because half of the barium and one chlorine ion it will be subtracted from this. So just substitute the values now. For the ammonium chloride, the value it is 2130. For the barium hydroxide, it's 460. So this is gonna be divided with the 2. And for the barium chloride, the value is 240. That is gonna be divided with the factor of 2. So solving this, the value we will be getting it as 2240 Siemens centimeter square per mole. This is gonna be the answer that is given to us in the option A over here. Right? Next one we have is this. It says the conductivity of the H positive ion in the aqueous medium is abnormally high. So you see same type of the question it was asked for the amide ions, right? That was formed from the ammonia solution. Now from the water we form the ions, that is H positive and the OH negative. These have exceptionally high conductance because of the proton jump, right? Grotthus mechanism it explains this. So this is gonna be the answer. Now next is we have this question. It says the equivalent conductance of a strong electrolytic solution. How is it varying with the dilution? We know that the equivalent conductance it is kappa upon the normality of the solution. Normality is nothing but the number of the gram equivalents upon the volume of the solution that we take it in the numerator. So with the dilution, the volume of the solution it is increasing. That means the equivalent conductance it is increasing with the dilution. So it increases with the dilution. That is option B. It is gonna be there. Alright. Moving upon to the next one, we have is this question. So again, you are seeing the plot is given. The first one, it is for the strong electrolyte that can be your extrapolated, and this second one is gonna be for the weak electrolytes that is go in the parallel direction to the molar conductance value. Hence, we cannot extrapolate it. So the statements that is given to us, we have to find the correct one in this. So first statement it says both the plots 1 and 2 it can be explained by the using the Debye-Huckel theory. It is not the correct. So the first plot that is for the strong electrolyte. This one we are saying that we are as we are decreasing the concentration or we are diluting the electrolytic solutions, the conductance it is increasing because the ionic interactions they are decreasing in them. And this is explained by the Debye-Huckel theory. This is explained by the Debye-Huckel theory. Right. Whereas for the weak electrolytes, the decrease in with the decrease in the concentration or with the dilution, the conductivity it is increasing because the degree of ionization it increases. Degree of ionization it increases with the dilution, and that is based upon your Ostwald dilution law. This is explained by the Ostwald dilution law, and this law is explained by your Arrhenius theory of electrolytic solution. This is based upon the Arrhenius theory of the electrolytic dissociation. Electrolytic dissociation. So you can see in this plots that we in the previous cases the questions when they were asking this was about what type of the electrolytic solutions are these, right? Now they have gone one step ahead. This is the past 2025 question only, this year only question it is there. They have gone one step ahead of this. That means now this time they are asking the theories also which are involved in defining these plots. Okay, so the plot one, it's explained by the Debye-Huckel theory, not the second plot is explained by that. So first statement is incorrect. B statement it says plot 1 and 2 can be explained by the Arrhenius theory of electrolytic dissociation. Again, the incorrect one. First is explained by the Debye-Huckel. So C statement it says now plot 1 and 2 can be explained by using the Debye-Huckel theory and the Arrhenius theory of the electrolytic solutions respectively. This statement is the correct because plot 1 is being explained by this theory and plot 2 is by this Arrhenius theory. So C is the correct answer in this case. D option also you can say it's saying plot 1 and 2 can be explained using the Arrhenius theory and then the Debye-Huckel theory respectively. So vice versa statement it is given. So it is not again the correct one. Okay. Now moving upon to the next, we have is this. So this type of the question again it was asked. So the term this now in the previous case this first term that was about the A they were asking. Now this is about the B term they are asking it now. So decrease in the conductivity it is there, but it is due to the electrophoretic effect. A was due to the asymmetric effect. Now B is due to the electrophoretic effect. So B into the lambda infinity into the under root C, it's correspond to the A option. That is the electrophoretic effect. Right. Moving upon to the next one we have is this. Walden's rule holds good for the large size ions. This is again now previously statement based questions were being asked from this that small ions are not for the small ions this is not useful because they are undergoing the solvation process. Right. Then the next time they gave it by taking the names of the large size ions. Now directly this question was asked that is Walden's rule it holds good for the large size ions. Okay. The next one we have is This question, it says the molar conductivity of the formic acid, this much molar it is given, is this much. The degree of dissociation and the dissociation constant, again, the similar type of the question has been asked that time the different electrolyte solution we were having it. So we are given us with the molar conductance lambda m, it is given as 40 Siemens centimeter square per mole, and the concentration value we are having it as 0.02 molar. Okay. We have to find this degree of dissociation, that means alpha value. For that we need is the molar conductance and the molar conductance at the infinite dilution. Right. So molar conductance it is given to us. We need is the molar conductance at infinite dilution. So formic acid we have it is HCOOH. Right. So for that these given ions, that is of the conductivity at infinite dilution for H positive, and this acetate ion it is already given to us. This format ion shall not be acetate. So for the conductivity for the H positive plus of this HCOO negative. So just add these values. For H positive it is 350 and this much is 50. So that becomes your 40 Siemens centimeter square per mole. Right, this is the value at infinite dilution. So alpha it is lambda m upon the lambda m at infinite dilution. Lambda m we are having is 40 and this we have got it as 400. So this is gonna be 1 by 10, that is zero point 0.1. So alpha value is 0.1. Now we need is the value of the degree of this dissociation constant, that is Ka value. This is nothing but the C alpha square. About this, how this dissociation is, this equation we have derived, I have told you in the previous questions. So concentration now we are having it as 0.02 and the alpha square, that is 0.1 square, it is gonna be there, so it is 0.02 into the 1 by 10 square is there, so 100 it is gonna come. So this is again the decimals will be coming. So 2 into 10 raised to the power of minus of 4. So this is gonna be the Ka value. So alpha is 0.1 and Ka value is 2 into 10 raised to the power of minus of 4. So the answer we are getting it as 0.1 and 2 into the 10 raised to the power of minus of 4, that is in the option D we are getting. Alright. Now moving upon to the next, we have is this question. It says in the given plots the conductometric titration, the volume corresponding to the points 1 and 2 indicates respectively. So mixture of the acids, again this type of the question was asked in the previous years also. So the first point it represents the strong acid neutralization, whereas the second point it represents the neutralization of this weak acid. So this is weak acid neutralization and here is this strong acid neutralization. Right? So the point one neutralization of strong acid and the second one is of the weak acid, that is given to us in the option B. Right? So this is the answer, is gonna be the answer in this. So this So that is it with your chapter, that was the electrochemistry. In this each and every single question that was asked from the year 2020 to 2025, all the questions we have discussed. If you have any doubt at any of the questions that we have done so far, you can ask me in the comment section. I'll surely reply to that. And if you have not watched the previous chapters that we have done so far, playlist is there, you can check that, or I'll provide the link in the description. Even for that you can get the access. So with this, your physical chemistry portion also we are done with this. We have covered now the organic chemistry portion and the physical chemistry portion. Alright, now that is it for this one. So we'll be meeting you in the next video now for the with the new chapter, that will be either your inorganic portion we will be starting or the analytical one. Which one you want first, you can let me know in the comment section. We will be starting with that. So for that also we will be discussing the questions. So make sure you don't forget to subscribe to the channel because many more videos are coming in this series. So that is it for this video now. We'll be meeting you in the next video with some new topic. Okay. So till then, bye bye.